Hello, Vinny. I don't think more people will be joining, so I will just start with today's session, and the recordings will be available later on. So, from the last couple of lectures, we are looking on this analysis of the stability of the closed loop systems. So, we covered this Routh array stability criteria based on Routh array. Then, in the last class, we discussed about this Bode stability criteria, which states that given a feedback control system, it will be unstable if the amplitude ratio corresponding to the open loop transfer function is greater than 1 at the phase crossover frequency. So let's assume if we are given any process and we have this controller and control element, and we are using a feedback control system to control the output. And if we find this amplitude ratio corresponding to the open loop transfer function of this block diagram at the phase crossover frequency, then it should always be less than 1 for the system to be stable. So the value of the controller gain is a decisive factor to ensure its stability. So how do we define these critical frequencies related to this phase crossover frequency and the gain crossover frequency? So we define it as the phase crossover frequency denoted by this omega pc is the frequency at which phase shift is equal to minus 180 degree. So given this block diagram corresponding to this closed loop system, we first write the open loop transfer function, then calculate the phase shift of that system. So phase shift is basically the phase angle of phase lag of all the blocks present in the block diagram. So if a transfer function is denoted by this a plus ib, then the phase lag we write it as tan inverse minus b by a. And if there are multiple block diagrams, then we simply add up those phase angles to get the total phase shift, and that should be equal to minus pi, that is minus 180 degree. Then similarly, the gain crossover frequency is the frequency at which the amplitude ratio is 1. So in the first phase crossover frequency, the phase shift is minus 180 degree, and in the gain crossover frequency, the amplitude ratio is 1. And as discussed, the stability criteria is that at this critical frequency, the amplitude ratio should be less than 1. Then based on that Bode stability criteria, we define this gain margin and phase margin. That is the margin of error that we have in order that the system doesn't get unstable. So the gain margin, we define it as 1 upon amplitude ratio. So this amplitude ratio should be calculated at this phase crossover frequency. And similarly, if we are calculating this phase margin, then we have to consider this gain crossover frequency, and corresponding to that, the phase margin is 180 degree plus the phase lag. And then we have the stability criteria. That is if both gain margin and phase margin are positive, then the control system is stable. If both are equal to 0, then the system is marginally stable. And if the gain margin and or the phase margin are negative, then the control system is unstable. So this is how we define this. Based on this gain margin, phase margin, and both stability criteria, we define this ultimate gain. So that is basically the ultimate gain is controller gain times of gain margin. So this gain margin is the design parameter that we provide to the system in order to ensure that the system won't become unstable corresponding to the noises or the changes in the inputs. So in the last class, we had looked upon few of the examples related to this Bode stability criteria. In this class also, we'll be continuing with those examples and also cover a few of the MCQ type of simple questions. So after we are done with this Bode stability criteria, we will be covering these processes with inverse response. Take a look at a few of the numericals related to it, and then move on to the instrumentation part. So now we'll be working on question by question, and whatever concept is in that question, we will be covering the instrumentation related to that question. So today we'll be looking into this operation of this pneumatic valve and the characteristics of the this pneumatic valves, and solve the questions related to it. So the first one is the simple theoretical question. So it is from grade 2021, question number 12, and the question is: a feed-forward controller can be used only if, and we have been given 4 options, and I have to find which of the following is correct. So does any of you know the answer? So in what scenario we can use the feed-forward controller? You can write it in chat box if you know the answer. So until now, we have studied 2 types of this control system. One was feedback control system, and the other was feed-forward control system. There are other more complex control systems such as this cascade control, ratio control, oxygenating control. But until now, we only studied this 2 control system: feedback control system and feed-forward control system. So the main thing to remember in both of this is in feedback control system, what we do is we measure the output, and based on that output, we take our control action in order to achieve that set point or what reject the disturbance. Similarly, in case of feed forward control system, we take the control action by measuring the changes in the disturbance. That is how we implement this feed forward control system. So from the given option, we can see that the option A is the disturbance variable can be measured. So in order to take control action based on this disturbance, we first need to measure it. That is the first option will be correct. That is the disturbance variable. If the disturbance variable can be measured, then only we can implement this feed-forward controller, or else it won't be possible to implement this. The second option is that disturbance variable can be manipulated. So this option is incorrect because disturbance variables aren't in our hand. So they can be called as a noise to the system, which can't be controlled by us, or which are uncertain. So they can't be manipulated. The option says disturbance variable can be ignored. So in any of this scenario, disturbance variable, if it plays the role in the changing the output of the system, then they can't be ignored. So we can't ignore this disturbance variable also. Then the fourth option is regulatory controller is not required. So even in scenarios where we use this regulatory controller, we can use a combination of both of this. We can use this feed forward controller. That is why the regulatory control, this option D is also incorrect. So option A is the correct option. That is, feed forward controller can be used only if the disturbance variable can be measured. So option A is the correct option for this case. Again, this is question number 31 of GATE 2021. So the question states that it is required to control the volume of contents in the jacketed reactor as shown in the figure. Which one of the following schemes can be used for feedback control? So in this question, they have shown us an application of this feedback control in order to control the volume of the contents in this reactor. So our main objective is to control the volume of the reactor. Corresponding to that, we have been given this P and ID diagram, that is piping and instrumentation diagram. So if you take a look on this diagram over here, we have been given few of this input. So this reactant can be considered as an input to the reactor. Similarly, cooling water is also an input of the system. And we manipulate this reactant by this valve V1, manipulate the cooling water flow rate by this valve V2. Then over here we have an agitator. Then this symbol shows the level transmitter. LT means level transmitter. So since it is connected to this reactor, we are measuring the level of this reactor using this level transmitter. So when we say I'm measuring the level of this reactor, basically I can calculate the volume using this level. So we are ultimately measuring the volume of the contents in this reactor using this level transmitter. Then we have this temperature transmitter, that is T101. TT means temperature transmitter, LT means level transmitter, V means valve. So this TT101 measures the temperature of the contents inside the jacketed reactor. Then we have these other two transmitters that are this TT, that is temperature transmitter T102, and FT is the flow transmitter F101, and they are connected to this cooling water line. So they will be measuring the temperature and the flow rate corresponding to this cooling water in the jacket. And ultimately for this product line, we are having this valve V3. Now in the given question, we have to control the volume of the reactor. So in order to control the volume of the reactor, first of all, I need to measure the volume of the reactor. So that is, I will be measuring the volume of the reactor using this level transmitter, that is L101. And in order to control the volume of the reactor, I can do, first of all, I can change the input flow rate, if that is in our hand. So by changing V1, I can change the volume of the reactor. So if the volume of the reactor increases, I can just close this valve and the level will be maintained. The other thing we can do is we can change the output flow rate using this valve V3. So again, if the volume of the reactor increases, and in order to decrease it, we can open this valve. So in order to control the volume of the reactor, we have to measure the volume by using this level transmitter, that is L101, and change and manipulate this valve V1 or V3, or we can do both, whatever is possible. So from the given options, we can see that the option A is measure L101 and manipulate valve V2. So this valve V2 is corresponding to this cooling water flow rate, and changing the flow rate of the cooling water won't affect the volume of the reactor, because this cooling water will flow through the jacket only. So this option is incorrect one. The second option is measure T101 and manipulate valve V1. So again, this T101 will be measuring the temperature of the reactor, and it won't have any correlation with the volume of the content present in this reactor. So this is also incorrect. Then the third option is measure L101 and manipulate valve V3. So that is what we discussed. We have to measure the content of the reactor using L101, and we can manipulate the product flow rate by using valve 3. So this option C is the correct option. And option D states measure F101 and manipulate valve V1. So again, this F101 is measuring the contents, is measuring the flow rate in this cooling water line. So this is our cooling water jacket, and F101 will measure the cooling water flow rate. So measuring this F101 won't be useful to us since we have to measure the contents of this jacketed reactor. So this option D is also incorrect. So from the given four options, option C is the most suitable one. That is, in order to control the volume of the reactor, we have to measure this level of this reactor and ultimately change the product flow rate. So option C is the correct option. So now this question is relatively general closed loop control. So the question states, which of the following is not a necessary condition for a process under closed loop control to be stable? So here we have been asked what are the stability conditions essential for a closed loop control. So until now, what we have studied is, first of all, if we have been given a transfer function, let's say g of s is equal to numerator upon denominator, the first thing we studied was the roots of the denominator must lie in this half of the plane. That is, they must have this negative real part. The other criteria we studied was based on this root array, and ultimately we studied this Bode stability criteria. There are other stability criteria also. So right now we only studied this one. So let's take a look on the following option. So the first option states that time term must be present in the open loop transfer function. So in each of these criteria as we studied, nowhere had we mentioned about this time present in this open loop transfer system. So even if we are having any open loop transfer function, any process, the presence of time term won't be a necessary or sufficient condition for this what closed loop control to be stable. That is, even if this time term is present, the system can be stable. So the given option is incorrect for our scenario. That is, it is not a necessary condition. Then option B states that roots of the characteristic equation must have a negative real part. So this one is the truth that for a system to be stable, the roots of the characteristic equation must have a negative real part. Then the option says all the elements in the left column of the root array must have the same sign. Based on this root stability criteria, we studied that we can create a root array using this term A1, A2, A3, A4. Then we have this capital A1, B1, and the elements in this first column must have this same sign. Then only we can see that the system is stable. So this is a necessary condition for stability. Then option D is open loop transfer function must have an amplitude ratio less than 1 at critical frequency. So based on this Bode stability criteria, we studied that this open loop, that this condition must be satisfied. So this option B, C, and D are necessary conditions for a system to be stable. And in the question, we have been asked which of the following is not a necessary condition for the closed loop system to be stable. That is why we can select this option A, since it is not necessary condition for the system to be stable. So do you have any doubts in any of these questions discussed until now? So now let's take a look on few of these numerical related to this Bode criteria for closed loop stability. So the first one is question number 51 from GATE 2017, and the question is the open loop transfer function of a process with proportional controller Kc is dash. Based on the Bode stability criterion for closed loop stability, the ultimate gain of controller rounded to 2 decimal places is dash. So over here we have been given an open loop transfer function and have been asked to find the ultimate gain of the control. That is, we have been asked to find the value of Ku using this Bode stability criterion for this open loop transfer function. So let's take a look on the video solution of this question. Let's just write the open loop transfer function. Open loop transfer function we have been given as GOL into Kc into e raised to minus of 2s upon 1, and we have been asked to find the ultimate gain, that is Ku, using Bode stability criteria. So according to this Bode stability criterion, we define this ultimate gain as the maximum value of the controller gain that can that can provide a stable closed loop response. So we define this if the controller gain is Kc, then we can write this Kc as Ku upon Gm, where Ku is the ultimate gain and Gm is the gain margin, and we find this ultimate gain such that this gain margin should be always greater than 1 to ensure stability. So using this Bode stability criterion, we define this ultimate gain as Ku. So that is what we have been asked in this question to find out. So for that, we need to find this value of gain margin. So gain margin, we can define it as the inverse of amplitude ratio at the phase crossover frequency. And that is gain margin is equal to 1 upon amplitude ratio at omega equal to omega C0. So for this, first of all, we need to find this gain crossover frequency. So we can find this gain crossover frequency as the frequency at which the phase lag is minus 180 degree. That is phi overall is equal to minus of 180 degree. So for this given transfer function, we can write the overall phase lag as, for this Kc it will be simply 0. For e raised to minus of omega tau, it will be simply minus of omega tau, and we need to convert it into degrees, so it will become minus of omega tau into 180 upon pi, and for this 1 upon s, the phase lag will be minus of 90 degree. So we can replace the values and find the value of minus omega. So this will become minus of omega tau is 2 into 180 upon pi is equal to, this will become minus of 90 degree. So we can write this as 360 upon pi into omega is equal to 90 degree. That is omega, we can write it as pi into 90 upon 360, that is pi by 4. So the crossover frequency we found out as pi by 4. Now we need to find the amplitude ratio of this transfer function at this frequency. So amplitude ratio will be simply multiplication of all amplitude ratio of this individual term. So it will be Kc into So for this e raised to minus 2s, the amplitude ratio will be 1, and for 1 upon s, it will be simply 1 upon omega. So now we can replace the value of omega, since we have to find the amplitude ratio with crossover frequency as pi by 4. So this will become kc upon pi. That is, amplitude ratio will become 4 kc upon pi. So from that we can write the gain margin as 1 upon amplitude ratio. This gain margin will become pi upon 4 times of kc. Now for this Bode stability criterion, we know that kc is equal to ku upon gain margin. That is, you can write ku is equal to kc to gain margin, and gain margin we found out as, let's just write kc as such, and gain margin we found out as pi upon 4 kc. That is pi upon 4 kc. Kc will get cancelled out, and the ultimate gain we can write it as pi by 4, or numerically you can write it as 0.785. So the final answer, that is based on the Bode criterion for closed loop stability, the ultimate gain of the controller rounded up to 2 decimal places, we can simply write it as 0.78. So in this question, we calculated the ultimate gain of the controller using this Bode stability criteria. Then the next question that we are looking is the question number 62 from GATE 2015, and the question states that consider a control system with open loop transfer function given by this equation, that is kc e raised to minus of 0.3s upon 1.5 s plus 1. In the above function, the prefactor of s is in minutes and kc is the gain of the proportional controller. The frequency for phase margin is 30 degree. The frequency for phase margin of 30 degree is 4.04 radian per minute. The value of kc for gain margin of 1.7 is dash. So in this given question, we have been asked the value of kc provided the gain margin of 1.7. So let's take this look, just look on this solution. So we were given this open loop transfer function, that is kc e raised to minus of 0.3s, 1.5 s plus 1. So this is our transfer function, and gain margin was provided 1.7. So this gain margin was calculated at this frequency, phase crossover frequency of 4.04 radian per minute. This is also given in question. And using all these three information, we have to find this value of kc. So what we know is gain margin is defined as 1 upon amplitude ratio. So this value of gain margin, we have this 1.7. Based on this, we can calculate this amplitude ratio using this transfer function, and then compare both of this equation to find the value of this kc. So that is how we do it. So there are this, you can say this three terms in this open loop transfer function. So the amplitude ratio will be multiplication of the individual amplitude ratio of each of these three terms. So if we are having this kc, the amplitude ratio will be simply kc. For this e raised to minus 0.3s, the amplitude ratio will be 1. And for this term 1 upon 1.5 s plus 1, the amplitude ratio will be 1 upon under root of omega square tau square plus 1. So that will become 1.5 omega whole square, 1 upon under root of 1.5 omega whole square plus 1. So that is 1 upon under root of 1.5 omega whole square plus 1, and this will be equal to 1 upon 1.7. Now the value of omega we have been given in the question as 4.04. So we will be replacing it in this equation, and then simply calculate the value of kc. it will come around 3.613. So yes, for the given open loop transfer function, we were already given this phase margin, phase frequency of phase margin for 30 degrees. This was 4.04 radian per minute. And using this gain margin, we calculated this value of Kc up to 1 decimal places as 3.6. So here we don't have any use of this phase margin of 30 degree since we have been already given this phase crossover frequency. Now let's take a look on this processes with inverse response. So we will be analyzing the response of the processes which exhibit an inverse response. So let's say if we are having two processes and they are connected in parallel according to this block diagram. So if U is my input of the system and Y is the corresponding output, and we are having these two processes, let's say P1 given by this first order system K1 upon tau 1 S plus 1, then the process 2 is given by this K2 upon tau 2 S plus 1, and ultimately my output will be, let's say, difference of both of these. So now if the response of this first process, that is P1, is given by this curve, that is, it will first order system that will keep on increasing, and if the response of this process 2 is given by this transfer function K2 upon tau 2 S plus 1, where the value of K2 is negative. If it is negative, then the response will be shown in by this below graph. So here we can see that both of these processes give us an output in opposite directions. So the resultant output that will be basically the result of both of these processes P1 and P2 can be shown by this overall process over here. So if tau 1 is greater than, so here we have been given this condition. So let's analyze this one by one. So first is tau 1 upon tau 2 is greater than 1. That is the time constant for first process is large than the time constant for second process. That is, the time constant is larger. That means it will take higher time for the system to reach a stability. So the first process will take higher time to become stable. That is being shown in this graph. So here you can see that it will become stable at over this point. Whereas for the second process, the time constant is less. So the system will achieve stability very fast as compared to the first process. So over here, we can see that the response or the output will become stable at somewhere over here, but that is at shorter time as compared to this process 1. So what will happen is if we are taking a resultant of both of this process, so initially, since the time constant for this process is very less as compared to the below one, initially we will be seeing the decrease in the output, and then ultimately this process will dominate, and the resultant as we go ahead in time will exhibit a positive curve. So initially we can see over here the response was negative, but after a short period of time the response will become positive. So this happened since this since this criteria we have been given, that is K1 is greater than K2, that is the process gain of the first process. The gain of the first process is higher as compared to the gain of the second process, but initially this time constant will play the role, and ultimately if we take on this resultant output at the final time instant, the process will become positive. So such a process in which initially the response is in other direction and ultimately the system will become stable in the opposite direction of the initial direction, then such a process we call it as inverse process, or the processes with inverse response. Now for this given block diagram, we can write the output as, over here we are having this plus and minus. So the first term will be subtracted from the second term, and we will be getting the output response as this equation, that is K1 upon, here it will be tau 1 s plus 1 upon k2 upon minus of k2 upon tau 2 s plus 1, and this is the input. We can simplify this to get such a form. So this we can, let's say, further write it as, let us consider this as tau a s, and this k1 minus k2 s k upon, it will become tau 1 s plus 1 upon tau 2 s plus 1. Over in this slide, this s is missing in both of these terms, so it will be present over here. So in general, the transfer function of the processes with inverse response, we can denote it using this equation, where tau 1 and tau 2 are the time constant of the individual processes present in the system, and k can be called as the difference of the process gain of the system, that is k1 minus k2, and tau a, you can say the weighted average based on this k1. Tau a, you can simply calculate this term. Now, other characteristics of this process, of the processes with inverse response, is that this system has a positive zero. So given any process with an inverse response, it must have a positive zero. So if more than one zeros are present in this in this system, then at least one of them should be a positive zero. Then only we can say that the system has a inverse response. So zeros are defined as the roots of the numerator, whereas poles, we already defined it as the roots of the denominator. So in this case, the zero will be the root of this numerator. So that will be k1 minus k2 upon this k1 k2 minus of k2 upon k1. So this is the zero of this process, and since this both of these terms k1 and k2 were positive and k1 was greater than k2, similarly we had this criteria for tau 1 and tau 2. So ultimately this term will always be greater than 0 for a process with an inverse response. So these two things we have to keep in mind. So given an inverse response, we can write the transfer function of this general form, and for any inverse response, we will be having a positive 0, and the response will exhibit a characteristic whereby initially the direction of the response will be different, but ultimately it will change its direction. So these are few of these characteristics related to this processes with inverse response we need to account for. Now we'll take a look on a few of these two examples related to this inverse response. So first is a straightforward MCQ from GATE 2016, and the question is, a system exhibits inverse response for a unit step change in input. So over here we have been given an inverse response for a unit step change in input. Which one of the following statement must necessarily be satisfied? Okay, so we have to find which of the following statement is correct for the inverse response for unit step change in the input. So the first option is, the transfer function of the system has at least one negative pole. So we didn't, so this negative, using this criteria, that is using the poles of the system, we can't comment on the inverse response of the system. We need to analyze the zeros of the system. So the first option is an incorrect one. The second system again states that the transfer function of the system has at least one positive pole. So this pole won't be sufficient to say about this inverse response. So both of these options are incorrect one. The third option is the transfer function of the system has at least one negative zero. So for the system to have inverse response, the zero must be positive. So this option C is also incorrect. And the fourth option states that the transfer function of the system at least has one positive zero. So this option D is the correct option. Since we studied for an inverse response, the transfer function must have at least one positive zero. So the correct option was option D. Now this is question number 31 of GATE 2019. So this question states that choose the option that correctly matches the step response curves on the left with the appropriate transfer function on the right. The step input change occurs at time t equal to 0. So over here on the right hand side, you can see that we have been given a transfer function. So basically a transfer function, we define it as you can say it output upon input, that is ys upon xs. And in the given question, we have been given a step response, that is xs is basically unit step response or 1 upon s. And on the left hand side, we have been given the step response, basically the output of the system, that is y of s. So y of s, we can write it as g of s into x of s. And we have to match which of this response corresponds to which of this transfer function. So let's take a look on the video solution of this question. So this is the last question that we are discussing today. We are solving question number 31 of GATE 2019 chemical. So over here on the right hand side, we have been given this transfer function, 4 different transfer function. And on the left hand side, we have been given the step response corresponding to the transfer function. And we have to find which one of the following plots belong to which of the transfer function. So let's take this step by step. So let's just consider this first transfer function. So over here, one is k upon zeta s plus 1 upon s tau s plus 1, where k is greater than 0, zeta is greater than 0, and tau is greater than 0. So to find the response corresponding to this transfer function for the step input, we have the step input u of s as 1 upon s. So we can find the response as y of s is equal to g of x into u of s, that will be 1 upon s into k times zeta s plus 1 upon s tau s plus 1. So one of the more complicated method to find the response is take the inverse of this equation, and then we will be having the relation between y and time, and then we can match which of the following option is matching. The other approach we can do is we can find the initial value and final value of all of this transfer function and then compare the values. Since in each of this plot you can see that the final value is differing and initial value is also differing. So let's just use this initial value theorem to find the initial value of this transfer function. So according to this initial value theorem, this y of 0, we can get it as limit s tends to infinity sys. So that will become limit s tends to infinity s upon s to k. Now from this term we'll be taking s common. It is zeta plus 1 upon s upon s square tau into 1 upon s. So this will get cancelled out. Now we can replace the value of s as infinity to find the initial value. So that will become k upon s is infinity. So 1 upon infinity will be, that is zeta plus 0 upon tau. So basically this value will be 0. that is at time t equal to 0, the value will be 0. Now we can find the final value, that is at time t equal to infinity. What is the value? So we can find it by limit s tends to 0 sys. So we can just put the value of s as 0 in this equation, that is s into 1 upon s into k tau of 0 plus 1 upon s. We will be putting it as 0 tau into 0 plus 1. This will get cancelled out. So over here we will be having 1 upon 0, that is basically infinity. So when time t tends to infinity, the value of the output will also keep on increasing. That is basically we don't have a bounded output. So from the given option, we can see that in the first option, the value is becoming constant at some fixed value. In the second option, the value keeps on increasing with time. In the last two options also, the value will converge to some steady state. So that is corresponding to this transfer function given by 1. The plot is shown in this Q block. So that is for Q, we have the first transfer function. Similarly, let us do for this second transfer function. So for the second transfer function, the response will be 1 upon s k zeta s plus 1 upon tau s plus 1. Now for initial value problem, initial value, we can write this y of 0 as limit s tends to infinity s into 1 upon s k zeta s plus 1 upon tau s plus 1. This will get cancelled out. We can take s as common, so it will become ks upon s, so zeta plus 1 upon s upon tau plus 1 upon s, as s will get cancelled out. And if we put this s as infinity, we will be getting the initial values k zeta upon tau. So over here we have been given that all these values are greater than 0. That implies that this value will also be greater than 0. Similarly, we will be finding the final value. It will become y of infinity, that is limit s tends to 0 k. So we'll be putting this as equal to 0, so it will become 0 0 plus 1 upon again 0 plus 1, that is 1. This will get cancelled out. So the final value will be k, that is some constant. So the initial value is a positive value greater than 0, and the final value is also a positive value, that is the greater than 0. So in the first option, the initial value is 0. Second option also, we have been given the initial value as 0. In the third option also, the initial value, we can say it as 0. And in the last option, we can see that the initial value is some fixed positive value, and that the final value is also some constant k. That is the second option. The second transfer function will correspond to the plot given by this s, that is s is 2. So until now we have q equal to 1, s is equal to 2. Let's just write it over here. q1 s2. And the third transfer function, that is g of s is equal to k upon tau s plus 1. Now this, we can remember that this is the first order transfer function. So for the first order transfer function, the response is given by such a kind of plot, and this plot matches this option P. So we can write this as, or corresponding to P, we are having third option. Now let's just analyze this fourth option also. We don't need for the final answer, but let's just understand it. So in the fourth option, we have been given the transfer function g of s as k times of zeta s plus 1 upon tau 1 s plus 1 on tau 2 s plus 1. So from the transfer function, we can see that we are having two time constant. That implies that there would be two interacting elements in this system, and also this transfer function matches the general transfer function form of this for this inverse response. So if any process is having components which provides us an inverse response, then the transfer function can be written as the form of k tau s plus 1 upon tau 1 s plus 1 upon tau 2 s plus 1. And if the zeros of this transfer function, that is the roots of the numerator, are greater than 0, that is, we can say that we are having an inverse response. And in case of an inverse response, what will happen is initially the response will be in one direction, and at the end the direction of the response will be another. So over here, if we have to find the roots of this equation, that is the numerator, that is zeta s plus 1 is equal to 0, we have this value of zeta over here is less than 0. So that is s, we can write it as minus 1 upon zeta. And since zeta is also less than 0, s will be greater than 0. That is, since the zeros of this transfer function is positive, we can say that this transfer function corresponds to an inverse response. Now from the given plot, this corresponding this option R, we can see that initially the output is negative, and then it will eventually reach a steady state at the positive value. That is, this is our inverse response. So corresponding to this option 4, we have this plot of R. So R will correspond to this 4. So over here we can just write R is equal to 4. Now we'll select the correct option from the given MCQs. So we are having this sequence of PQRS, so that is 3, 1, 4, 2. Now from the given option, we can see that 3, 1, 4, 2 corresponds to this option B. So option B is the correct answer. So we looked on this question in which we had to analyze the response of the system given the transfer function, whereby we had this first order system inverse response and the other two custom transfer functions. So we use this initial value theorem and final value theorem to find the initial and the final state of the system, and then just check them with the plot to find the correct transfer function. So in the next class, we will be looking onto this instrument. We will be starting with instrumentation. First of all, we will be studying this pneumatic valve and look on few of these questions related to these pneumatic valves. So that was all for today's class. So ideally, each of these video lectures should be uploaded on this NPTEL website, but I'm not sure why they haven't uploaded it yet. So for phase 1, they had this recording link. For phase 2, they haven't provided the video recordings yet. So I have this all these questions that I'm solving uploaded as video solutions on this channel, where I'm also uploading the video recording of the entire session. So right now I haven't done it for the last class. I will just do it right now for this today's class and the last class, and you can find it in this YouTube link. I'm uploading this, mentioning this link in the chat box. So do you have any questions related to any of the topic related to this process control, or in general related to other subjects of Git? Then we can discuss it in the next class. So right now in this process control, we have covered this process modeling stability criteria. Now we are moving on to this instrumentation part, but we will be also covering few of these questions related to this general control strategy. So if you have any questions, you can write it in chat box, or else we can end today's session. So, yeah, today's session. So thank you for joining.